All right, so thank you and good morning, and thank you for the invitation to be here to present to you all. So my name's Professor Andrew Paluch. I'm a faculty here in the Department of Chemical, Paper, and Biomedical Engineering at Miami University in Oxford, Ohio. And I am thrilled to be here to talk to you all today about, as the title says, building concepts and confidence in undergraduate education by use of a process simulator, and specifically CHEMCAD in our case. And so the presentation is going to be more based on my experience and opinions, and hopefully it can be of good use and benefit to you. So in terms of the outline for this presentation, we'll start with an overview and motivation for this work in terms of why we're motivated, interested in implementing Process Simulator within our curriculum here at Miami University, and the positive impact that CHEMCAD can have on our base chemical engineering education. We'll have time to look at a few examples from courses and from my experience here. And then I'll pass things over to Whitney, who'll be able to discuss more background about CHEMCAD and some additional resources that are available to you. And to start with kind of the intro and motivation, so I just want to share with you an example that I always enjoy doing every year here. And so this would be, a problem that I've often deployed at the junior level, but I could easily see at the sophomore level in a materials and energy balance class. And so we live about, our campus is about 6 miles away from Houston Wood State Park. And Houston Wood State Park, every year at the beginning of March, has an annual maple syrup festival that I always encourage the students to go to and promote. And so it's a great festival in general. But as a chemical engineer, it's really fun, right? It's fun in that we get to go experience the process of maple syrup production. So when you go to the park, you can experience the collection of sap from the maple forest. We learn from the rangers that the sap that's being collected is 2 to 4% sugar by mass, and that standards require that for finished product of maple syrup, they need to concentrate that down to at least 66% sugar by mass. And so approximately it takes 40 gallons of sap to make 1 gallon of finished maple syrup. And so we see the collection process where we're educated in maple syrup production, and then the tour ends in what they call the sugar shack. And so at the sugar shack, we see the continuous evaporator that the park operates in terms of producing maple syrup. And it's interesting when you first enter the room. Essentially, it's almost as if you're in a steam room, right? And I have 40 gallons of sap being used to make 1 gallon of maple syrup, right? So if I'm trying to produce 1 gallon of maple syrup, I'm essentially vaporizing, right? I need to evaporate 39 gallons of water from that sap solution. So it's a energy intensive process. The students see firsthand by the large generation of steam that's happening in the sugar shack. And so we encourage the students to go out. It happens over the course of 2 weekends. And then when they return to campus, we have a fun exercise of, well, let's model this process, right? And this can be handled right as early as students in the sophomore year, right? I can just do a simple mass and energy balance, right? And I could calculate, say, the required heat duty for this process. But we model the process. We model our evaporator essentially as a flash drum. We can perform a mass and energy balance on it and calculate the heat duty. We can then take it a step further, though, right? So part of the benefit and appeal of using CHEMCAD is, well, we can perform a mass and energy balance on this process. Okay, we can then translate that to CHEMCAD, and we can model this in CHEMCAD. We can intuitively model and have CHEMCAD perform the relevant mass and energy balance calculations on our system, and we can calculate that large required heat duty for this process. But then what CHEMCAD does is not only allow us to model this existing process, but part of the fun is it can allow us to challenge the students and fully tap into their design skills, right? And so with this simple example, we can say, okay, you went and you experienced, right, this process, right? You saw the large amount of steam that's being generated, right? We calculate the large heat duty required for this process. right? And we have a discussion about, what the inefficiencies of this process are and how you might improve it. Okay. And what's nice is by having this base model then set up in CHEMCAD is the students can actually go at it as then design engineers and try and implement strategies to make the process more efficient. And then they can see firsthand, right, the improvements on this process that they then went and witnessed, right, over the past weekend in this fun experience. Right. And so some students will, take my feed stream and they'll implement a membrane to try and remove, large amounts of water so that they don't need to vaporize as much in the evaporator. Or some, right, as in this example flow sheet here, will have remembered this experience of this large amount of steam being generated and say, oh, it'd be great if I could somehow capture the steam. So thinking in terms of, heat integration without using the words quite yet. All right, if I could capture that, the steam that's being generated and use that to preheat my feed stream, right, so I could decrease the heat duty of my process. All right, and what I find, really rewarding from this experience, right, and this can happen as early as sophomore year, is we can model the process, right, in a traditional way. We could perform our mass and energy balance for the process. We can then set this up in CHEMCAD, right, and it's a pretty straightforward simulation, just single flash drum where we have a feed stream and then two product streams from our flash drum. But then we can really challenge the students to think like design engineers, right? So how could you make this process more efficient? And then not only how could you make it more efficient, from a conceptual discussion, but then they could actually go into CHEMCAD and they could try and implement these and directly see the effect, right? They can add a membrane, right? Even though they haven't quite studied membranes in their classes, right? They could implement, right, this strategy of thermal integration, even though we haven't, discussed thermal integration yet, which usually comes later on in their senior year. And so, from this simple example, right, one of the appeals of CHEMCAD is it allows students to solve, all right, some complex problems, but really, transforms, students from the traditional sense to kind of, design engineers, right? We can allow them to think more creatively and solve some more realistic problems. And so kind of a big overview of kind of, how I think about things, right, as we work to develop, curriculum here at Miami is, with that, example from maple syrup production, in mind is, Miami University, every other university in the US, right? Every other chemical engineering, department in the world, right? What is the main goal and mission, right, of your department, right? And in general, right, all of us, right, the main goal or mission of our department is to prepare students for successful careers in industry. All right, so our goal is to prepare students for successful careers in industry. Okay, well, what's the challenge? Well, the challenge is well, typically the courses that we teach are designed based on our own experiences as an undergraduate or based on recommendations of a senior faculty member. Okay, and so, a challenge is okay, our goal is we want to prepare students for successful careers in industry. Okay, a challenge, though, is that oftentimes our courses are starting with older, right? I won't say outdated, right? But typically we have older, right, based curriculums, which are based on our experiences when we went through a program as an undergraduate or the recommendations of a senior faculty member. The other challenge that we typically face is that, say course creation, organization, material preparation requires a large investment of time, making faculty slow or reluctant to change, right? And it's not even just the course creation. It's just, as I'm a faculty and I teach a course, even when I have, say prepared material for a course, you still only have so much time, right? Even if I have a fully prepared class, a course, I still need to deliver the course. I still need to develop assessments. I still need to grade student work. I still need to field, questions from students in office hours on top of my service and research obligations to the university. All right. So as a faculty, our time is limited, right? And so, we're a lot less, we're slow to change. And this is problematic because, the chemical industry continues to change and evolve. And so chemical industry continues to change and evolve, right? Faculty are typically starting with older material when they teach a course and are slow to change. Okay. And so if our goal is to train students for successful careers in industry, right, the question becomes is, well, are we meeting that goal with our current curriculum? The other challenge I see and think about as we think about curriculum is student retention, right? And so you can think about this in a number of different ways, right? But the question that I pose, first is, what are the common reasons for undergraduate students to leave the chemical engineering major? And so, the first kind of bucket I think about are foundational courses. And, this is a challenge with engineering in general, in that we have a large number of foundational courses where, the first essentially year and a half, the students are primarily taking courses outside of our department. And so, what I mean by foundational challenges is, as an example, a student that, say, didn't perform well in calculus, right, dropping out of their major in chemical engineering because they have this idea in their head that if they didn't perform well in calculus, they're not going to be able to perform well in upper level chemical engineering courses, right? And then they're not going to be able to perform well, right, in a future career as a chemical engineer, right? As if, they have this idea in their head that once they graduate, they're going to be sitting in a cubicle solving problems by hand like they do in their general physics and calculus classes. All right, so a retention challenge can come in these foundational courses where a student doesn't necessarily perform well, right? And then they have this thought or belief that just means they can't be an engineer, right? And it's frustrating because they declared engineering as a major for a reason, right? But now it's say a math or physics class, which is preventing them from, fulfilling, right, that goal. The other place where it comes in is, I think about our core chemical engineering courses, right? So as a chemical engineer, I would say our curriculum is challenging and difficult, right? And, part of the challenge comes in, kind of connecting to similar issue from those foundational courses is a lot of our assessment in our core classes is often based on quantitative exams, right? And so it kind of propagates where, if a student isn't very strong or had a poor experience in, say, differential equations, well, that carries over. And if I have, quantitative heavy exams in, say, my, kinetics and reactor design course, that the student could then end up struggling on the exams that I'm using to assess them, right? And so it becomes challenging, even more challenging as it propagates the curriculum. And this can become challenging too, in that students, don't fully realize the value of their conceptual knowledge, right, and the real value that that's going to have, right, post-graduation, maybe probably even more so than their quantitative skills. Another challenge I see is that in our core curriculum, our problems that we ask them to solve are often limited in complexity. So I think back to that simple maple syrup example. All right, so mass and energy balance, and even my separation process, right? We could design, right, an evaporator, but actually then thinking about how I could optimize, right, that evaporator, right, are kind of beyond the limits of course, right? Or in a separations class, right, I could perform an analysis of a distillation column, right? But the students aren't analyzing a complete gas separation process where they can see that distillation column, right, in use, right, connected to additional units within their plant. And again, right, we have this challenge where, I don't know what it is, but, when I have students, even, sometimes in their junior year, they have this idea in their head that when they graduate, they're going to be sitting in a cubicle solving problems by hand, right? And so they become frustrated with their courses when they're not performing well, in that they end up leaving chemical engineering because they don't think they're going to be successful post-graduation. And then when it comes to these complex problems, right, and things of that nature, and the value of conceptual knowledge and understanding is they don't really fully understand, right, the talents that they have and what they're capable of when they get to senior year and are looking for jobs in the future. And we have tried to address some of these issues, and so there's a big push in terms of implementing computational methods in the curriculum, but primarily that's been focused on things like Excel, MATLAB, and Python. The hope is this could give us the ability to solve more complicated, realistic problems, but could also give the students more confidence, right, in terms of having these tools that could help if they struggle with any of the math. But at least from my perspective, here, right, the use of process simulators, right, hasn't been, kind of put up front and center, right, as these other tools have, right? And so, I'd ask, well, what about process simulators, right? And what role can process simulators play in all of this, and how can that help us? Now, co-ops and internships, right? Those are great, right? In terms of students getting out of campus, getting a better feel of what they can expect post-graduation, realizing their talents and capabilities. But while that's great experience for the students, right, and addresses this, it doesn't, it still, right, leaves me asking though. We can still though make changes and modifications to our curriculum, right? Besides just this co-op program, right, to better prepare our students for these careers post-graduation, right? So it doesn't completely, free us of, well, we should just keep using, say, outdated curriculum because the co-op program will fill in the rest, right? It's no, right? As a faculty, right, our main mission is to prepare students for successful careers in industry, right? So co-op's great, right? But we should still think about modifying our curriculum. And then, yeah, we do have a capstone design course, or everybody's going to have a capstone design course, which is typically a process design course during the student's last year. But that design experience where process designs or process simulators typically first introduced doesn't happen until their senior year towards the end of their curriculum. And so, again, big focus is on, what about process simulators, right? And how can that be used and help us to meet some of these goals and overcome some of these challenges? This is a quote that Whitney pulled from a testimonial that I prepared for CHEMCAD. But it's post-graduation, students are not going to design a distillation column using a pencil and paper. They're going to use state-of-the-art computational tools such as CHEMCAD, right? So it's important that we, right, as a faculty, introduce students to these state-of-the-art methods, right, as an undergraduate, right, so that they're better prepared for these careers and to be successful post-graduation. And so what I have here is just a picture of, typical or conventional four-year curriculum. So it's simplified version, four-year curriculum for a chemical engineering major. And so, curriculum for chemical engineering major broken down by year. And so in general, in year one, we're primarily taking foundational courses. So our calculus, general chemistry, general physics, intro to engineering, 1 or 2 semesters, trying to make that connection. Year two is still pretty much split, right? We still have some foundational courses, say differential equations and organic chemistry. And then we start to get into, core chemical engineering with our mass and energy balance and engineering thermo. Year 3 is full on core chemical engineering. And then year 4 is typically where we start to transition to more of a design-based courses. So kinetics and reactor design, process control, and process design. And what I'm doing here with my color kind of scheme is the uncolored, right, circles, right? Those are courses, core courses outside of our department, so kind of outside of our control. And then process design, I have colored red, right? And the meaning of this is just process design is our, kind of one course where we really fully, introduce students to the design experience. And it's that one course where students are primarily introduced to a process simulator, right? So within process design, right, we're going to heavily make use of CHEMCAD. Okay. A challenge, though, is yellow corresponds to all of our other core courses. And in general, especially depending on who's teaching it, at least here, the students aren't introduced to CHEMCAD at all, right? Or they're not introduced to a process simulator at all. And so we have all these core courses in which students are learning base material, which is great. And then we get to this final, design experience the last semester, and it's there that students are introduced to CHEMCAD, right, and go through a full design experience. And so what I would advocate is, how can we change this so that within all of our core chemical engineering courses, we have some introduction, or the students are touching, right, a process simulator, working or interacting with the process simulator in some way, right? So that we're not just leaving it for this final design experience here last semester. And so not promoting, essentially anything drastic, right? But what I would encourage or promote, or to try and think about, is are there small changes or small additions that we can make to our core courses, right, leading up to that final, design experience, right? And the idea that, these small changes that we can make throughout the curriculum, beginning as early as year one, right, but definitely in year two, are there small changes or additions that we can make where we're introducing students to our process simulator, right, with the idea that small changes can have a large compounding effect, which will elevate our students, right, throughout the curriculum, and then really elevate them in that final cumulative design experience that will happen last semester. All right. And so not drastic changes, but trying to think about small changes that we can implement in each of our courses that can have a compounding effect, right, in terms of giving students confidence, right, demonstrating their ability to, I'm really struggling in my transport class, right, solving problem X, right, but having that reassurance that there's these tools called process simulators, right, that can, are capable of performing these calculations that can assist and help, right? So, confidence, right? A tool, right, that the students know is there, right? So giving them confidence, in addition to using and getting comfortable working with to build up to that final experience. And so what I want to do next is just go through a couple of select examples, some non-conventional, and just think about small things that we could do within a class and how we could change a class with, small amount of effort and change. And so here's just an example from engineering thermo. So this is, thermo one, first and second law balances and closed and open systems is primarily what we cover here. And so, here's just an example where towards the last third of the class, at least here, we start to cover balances and open systems. Well, when we talk about balances and open systems and open flow devices, right, we can, then jump over to CHEMCAD and demonstrate to students, well, how we can model a compressor, right? And so just look at a simple example of modeling the adiabatic compression of steam. And so the spreadsheet is incredibly simple, but we can demonstrate how we can perform the calculation. We have this process simulator, right, which can perform this calculation. But then we can also draw some interesting comparisons to how we're solving these by hand in class. All right. So sometimes I joke that when I teach engineering thermo, when students graduate and leave, one of the skills that they really feel like they've mastered, or one of the things that they really, kind of talk about of, engineering one or thermo one, right, I learned how to do this, right? And that one thing that they often say is, well, I learned how to, read and interpolate in the steam tables, right? That's great, right? But post-graduation, are you going to be reading and interpolating in the steam tables? So reading and interpolating the steam tables, right, has value, right? Because the students need to be able to know if their, system is fully defined. And so it's really useful, right, in terms of, understanding and their system, right? But what's interesting then is we go over to CHEMCAD, when we set these processes up, it's, well, there's no steam tables, right? Well, what is CHEMCAD doing, right? And so it's makes this connection to equations of state, right? So we can have a conversation about equations of state and how CHEMCAD is calculating all of the properties of interest that I need via an equation of state, right? And not making use of the steam tables. So it's useful and helpful, and so that students see how, well, in the real world, how these calculations, say, are done, right, devoid of steam tables, right? We can make the connections to steam tables and how equations of state are used to generate those and their value. But we can see, right, how these calculations are actually done and performed, and how one can leverage an equation of state. And then it also leverages or motivates discussions later on once we actually introduce equations of state and property relations, because that's what CHEMCAD's actually doing, right? So it can make the connection of how calculations are actually done. We can model these systems. We can get, similar answers without interpolating the steam tables, and have that conversation, and then use that in terms of motivating discussion later on when we talk about equations of state and property relationships, for why that's useful and important and valuable, right? That's what's happening under the hood here. But we can, set up and analyze our compressor. We can, turn knobs, right? We can change its operations, right? So we can readily, change knobs and look at effects on our inlet and outlet streams and the performance of our system. We can generate stream reports. And so here's just an example of all the different types of reports that CHEMCAD can generate, but we can, generate a report for our unit op, which in this case is a compressor, and then we can generate information about all of our streams, and CHEMCAD will calculate anything and everything you could possibly want to know, right, about your streams. Okay, again, leveraging an equation of state. And so, this would just be a simple activity that we could introduce in, say, engineering thermo 1, where students can, gain awareness of this tool, this process simulator, gain some appreciation for how it's working, right? And then make some connections from their class back to that, right? And then also have some confidence leaving class of, what I try and promote, or what's most valuable in class, or, big takeaway is that I want to make sure you conceptually understand, right, the material. You conceptually understand these flow devices, right, and what the effect of changing different variables are on that resulting performance, right? So then when I come over to CHEMCAD, right, it's going to make me a better design engineer as I think about tweaking and optimizing these processes. Here's an example from transport. And so, common problems that we solve, right, in fluid mechanics is trying to calculate pressure drops, right, across, say, a section of pipe. And so if I'm trying to calculate the pressure drop across some section of pipe, it's going to involve doing things like calculating the Reynolds number so I can identify my flow regime. I'm going to need to identify, say, the material that my pipe's made out of, so that if I have the material and the dimensions of my pipe, I can get my relative roughness. And then that, along with my Reynolds number, I can get my friction factor, which I would generally get from a Moody friction diagram. And then I can, go and calculate and solve my problem. But again, right, it's, well, post-graduation, if I had to do something like this, am I going to be sitting in a cubicle, using my Moody diagram and solving these problems by hand, right? So introducing them to, well, CHEMCAD can do this, right? CHEMCAD has a unit op, which is pipe. And so, here's just a simple example where I've added a pipe to simulation. I have a single inlet and outlet stream. And then you could go in and you could specify, right, anything you want about that pipe, right? I can specify the material it's made of, the size, the length, and CHEMCAD can then, ultimately calculate, the pressure drop across that section of pipe, right? It can do the calculation for us. So now it's important that we, have this conceptual understanding from when we solve the problem of what, the inputs are and what the output is. It's also important, to think about the roughness of material and what we expect the effect it to be in, the roughness and the pressure drop. But knowing that there's a tool, like this, right, that can solve these. What I have highlighted here in red, or boxed in red, is there's even 2 other tabs where you could specify different valves and fittings that might be within this process. And so this is just a simple example where it's just, pressure drop across a single section of pipe, but you could build this up. You could, take your feed stream and you could have a divider. You could split it up into 3 evenly, streams with even flow rates, send those to 3 pipes in parallel, and then bring those back and look at, what happens now if I have, say, 3 pipes in parallel versus 3 in series, or 1 long pipe. We can start to play experiments like that, and the students can test their conceptual understanding of the material from class. You could build complicated piping networks, right? You could build complex systems where the problems would start to become intractable in terms of solving by hand, say in class, but with CHEMCAD, right, where it's intuitive, right, I can set this up visually, and I can, solve and analyze these complex systems. This can also be a nice lead-in where I'm not sure in your curriculum, you might talk about pumps in your transport class. Pumps might be discussed in a separate unit ops course. But as you develop these complex piping networks, that could be a great introduction in terms of talking about pumps and how you might, size, a pump for a particular system. And then, what, in CHEMCAD, you can actually size and design a pump, right, for that, system that I, say, created in my transport class that I'm carrying over. Separations, right? So here's just an example of modeling an absorber. And so I have, some gas stream with some contaminants, which I'm calling stream 2 here, entering my column, and my absorber, my separating agent's my solvent, which I'm going to contact with that gas to try and absorb the solute. So that stream 4 coming out the bottom is going to be my solvent plus solute. Then I have some clean treated gas coming out the top of my column. So we can talk about absorption in class. We can model it using a McCabe-Thiele diagram, right? And McCabe-Thiele diagrams, right, are great because I can, discuss or visualize of, what happens as I change particular knobs within my column, right? So as the solvent flow rate increases, I can visually see what the effect is on my operating line, all right, and how we would need, say, less stages, to achieve, a given separation. And so, we can discuss these in terms of McCabe-Thiele, but again, students aren't necessarily going to be designing distillation or absorption columns using a McCabe-Thiele diagram. But as we go to CHEMCAD, we can demonstrate how to realistically solve these things, or how we can solve these in CHEMCAD, and we can make the connection back to our McCabe-Thiele diagrams of that conceptual understanding of understanding what knobs to turn, and then using that in terms of designing and sizing, right, our column, right, and also performing virtual experiments where we can check back to our McCabe-Thiele diagram to confirm that understanding. And we could do some, more sophisticated things. And so what's behind this window is I've just added what CHEMCAD calls a controller to my exiting solvent stream, and I'm going to operate it in a feedback mechanism. So I kind of think about this as like goal seek. And so we can, ask what if scenarios. And so here I'm going to use this feedback controller, and I can use it to, change the inlet solvent flow rate until the, solute mole frac in my exit stream is equal to a particular value. All right. And so we can use things like controllers to try and, optimize or set settings for my column. We can also make use of sensitivity analyses. And so this is from the analysis menu and in CHEMCAD. So, under analysis, I can set up a what if analysis. And in a what if analysis, I could say, here's my base steady state simulation. I want you to run my simulation, say 300 times, or 100 times, where you vary the solvent flow rate from 200 to 500 kilomoles per hour, and 100 equal steps. And then I want you to track the mole frac of my solute in the exit stream for all those cases. And then you can plot the results, right? And so, we can use these sensitivity analyses, right, to try and reinforce our knowledge of looking at the effect of turning particular knobs, right, on that column performance. And so here, in a matter of a couple seconds, CHEMCAD's able to solve the simulation 100 times, plot the results, right? Something that would be a little more challenging to get something quantitative like this by hand. All right, we could then do a similar thing and talk about stripping columns, but then in my opinion, where CHEMCAD can really elevate things is, well, in a separations class, we could talk about absorption and we can model absorption columns. We can then talk about stripping columns and model stripping columns, say using McCabe-Thiele. And then, in a course, we might discuss, how an absorber and a stripper might be used, together, right, in a gas treatment process. But with CHEMCAD, we can actually start to model these things and see these things take form in real life. And so, when I talk about absorption, stripping, extraction, right, when I talk about separations in general, I talk about the separating agent. So an absorption, stripping, extraction, separating agent's the solvent, all right, something like distillation, it's heat, right, it's energy. And so we can start to think about things like, well, my absorber, okay, so I have the solvent going in, my separating agent in stream 1. And in stream 4, now I have my solvent plus that solute that I was trying to remove from my gas stream. Okay, what do I do with it, right? Well, it'd be great if I could somehow recover, right, that solvent so that I could recycle it and send it back to my first column, right? Otherwise, this is going to be a pretty expensive, process. And so we go through, well, if I have this stream now where it's a solvent plus a non-condensable gas, well, I can make the connection now of, well, how could I, try and remove that non-condensable gas from my solvent? Well, I could think back to what we just talked about in terms of stripping columns. right? And I could, put that in series with the stripping column, all right? And then once we get the stripping column working, we can actually, realistically model, right, this entire process where I can then try and, um, take my solvent and send it back, right, in a recycle stream back to my initial absorption column. All right. And this is something I definitely wouldn't be able to solve by hand in class, right? I could have a conversation. But sometimes it's, kind of this, universal design sort of strategy, right? Every student's going to learn in a different way. And so I could describe the process to students, I could tell them about it, but there's just something about, students actually setting this up and playing with it in real time in CHEMCAD that makes a huge difference, right? And so we can go from just modeling an absorber and stripper in by hand using the Cape Thiele to putting these two units in CHEMCAD, connecting them, and then actually designing some realistic gas treatment process. And the amount of effort that goes in, right? This, when I've done this in unit ops, is we have lecture during the week, right? But then I have some small amount of time reserved for the end of class. We get the intro to CHEMCAD, which is complemented by videos that I have them watch outside. Here's an example from thermo. And so thinking a little more, non-traditional. And so there's lots of, ways in which we could use CHEMCAD and thermo. Some that I like are just in terms of, well, so let me pause for a second. So I talked about kind of engineering thermo 1 here at Miami. Engineering thermo 1 is first and second law balances on closed and open systems. We also talk about property relationships and equations of state. Thermo 2 is more about phase equilibria and mixtures. And so CHEMCAD, right, has some really awesome abilities in terms of visualizing phase diagrams and understanding sensitivity to models. And so here's just an example where I just created a flow sheet and I added ethanol and water to my system. And, under my thermophysical menu, all right, there's an option to generate an azeotrope report. So for that binary system, it can, if you specify temperature or pressure, it'll tell you if there's an azeotrope, right? And this is even a cool tool to see here, because then when we get to design, I like to do a lot with azeotropic separations. And so, there, if I'm thinking about, say, trying to find an entrainer for the homogeneous azeotropic separation, right? This is a great tool. If I had a binary, it can look at each binary pair and tell you if there's an azeotrope that's formed or not. Another tool that's pretty fun is in thermo. During the semester, I like to have the students fit BIPs or parameters for an excess Gibbs free energy model to reference data. And that would often involve having the data in Excel, then asking the students to perform a data regression in Excel or MATLAB. Well, CHEMCAD can do it, right? So there's this option here for BIP regression. And here's just the window with options. But one of them is you can provide TXY data, TXY or PXY data, and you can select an excess Gibbs free energy model, and CHEMCAD will regress BIPs for that model or parameters for that model. And then not only that, once CHEMCAD has knowledge of the model, we could generate plots and phase diagrams with them and actually use those regress parameters in the design of processes. And so kind of tying in on the home screen, there's also this option to develop plot charts, just like we had reports before. And there's a large number of plots available. But even under TXY, PXY is fun for thermo in terms of generating phase diagrams and let students visually see phase behavior. Here's just an example of one feature that I like is that when I generate, in this case, a PXY, so the default recommended excess Gibbs free energy model for ethanol water is NRTL. We can have conversations in class about why does CHEMCAD recommend it? Well, because CHEMCAD has a bunch of internal data. They try fitting all the excess Gibbs free energy models to it, and that's one that gives the smallest error, which is in line with what we know from Decima for aqueous systems. And so we can have conversations with how they come up with that selection. And then here's just an example, but you can add other models. And so you can add other excess Gibbs free energy models built in CHEMCAD and plot those along with that recommended, or even get rid of the recommended. And so here I can add in Rail's law, right? And so we can plot, the result. And so here I see, Rayleigh law. So Rayleigh's law, my bubble lines, my purple line, my straight line, representative of Rayleigh's law. Then I see my dew line, the yellow line. And then we see our actual system, which is the blue and red. And so we can see these large deviations that we have from Rayleigh's law. We could talk about these deviations, right, in relative to that, perfect straight line, which is my bubble line, right, in terms of, deviations from Rayleigh's law and what that physically means. And then also just connecting it back to, well, while in our mass and energy balance course, we solved everything using Rayleigh's law, we shouldn't do that, right, in reality, because that's going to have some, large effects. Now, one thing I did want to mention, just because it just dawned on me that I forgot, is thinking back to engineering thermo in my other classes, is a thing that the students often struggle with are units, right, as well. And engineering thermo is a big one. The course we teach is joint with mechanical engineering, and so there's a lot of English units in the course that we teach. But it's one beautiful thing about CHEMCAD is when I say model that compressor, or if I'm modeling my stripper or absorber, is that on the home tab, there's a button that I can click called engineering units. And if I solve my problem and say SI units, but someone else wants the solution, but in English units, or one parameter is given in English units, I can go into engineering units and I could, just with a click of a button, change to a different system of units, and my entire flow sheet will be converted, for you, right, in terms of taking that part out of it. But getting back, right, the idea is, as we, give students these small experiences in all of their classes, it's, one, hopefully giving them confidence, right? Giving them confidence that if they sit there in their kinetics exam and they are struggling solving that differential equation, confidence that that doesn't mean I can't be a successful chemical engineer, right? Okay, we've got these great tools like CHEMCAD, which can solve these complicated problems accurately. What's really important is that I have this great, making sure that I really understand the concepts, have a great conceptual understanding, right, of the material, so that I can use, right, that tool that's going to help me solve real problems, right? Give them confidence as well, so that when they go and interview for a job, right, they realize the value that they have, right? Oftentimes, it's students don't fully value their talents or what they're capable of and how incredible they are, right? What they actually learned those 4 years, right? Oftentimes you sit here for 4 years, and it's almost like, I always tell students, like, they don't look back and reflect on, how far they've come. But it's also, they don't really realize what they're capable of, right? And so hopefully by using this process simulator throughout, right, they can gain confidence, right, in terms of solving problems, but then confidence in their capabilities, when they move on to job interviews. Hopefully it can also help them in terms of, better mastering material and concepts, right? So the example of, modeling an absorber, right? So we can give a lecture in class about the effect of our different control parameters on the absorber performance. They can perform a McCabe-Thiele analysis and see it for themselves firsthand, right? But for some students that still, might not click, right? But then maybe if they put it into CHEMCAD and they're physically, turning these knobs in CHEMCAD, maybe then, right, in this third way that they're seeing it, right, it begins to click. But then not only that, it gives them a way of testing themselves. So before an exam, they can start to ask themselves questions, right, and test the answers using CHEMCAD. And, again, bringing it back to this retention issue is, this confidence, right? I didn't perform well in calculus, but that might have been how I was assessed. That might have been the format of the course. It could be instructor dependent. There's a lot that goes in there. But just because I have a C in, say, calculus, that doesn't mean I can't be a fantastic design engineer. And then, the hope is with these small pieces throughout the curriculum is that when they finally do get to process design, they're able to quickly jump in and solve large, complex, complicated problems. So here's just an example from not spring 2024, spring 2023, where within the first couple of weeks in the semester, we had students modeling or designing a cold methanol process. And so, here's just a sample spreadsheet from, within the first couple of weeks, in which they have, process, which is using, reactors. We have separation units. We have compressors and heat exchangers, right? So they're able to take a lot of this material that they've seen throughout and more easily and quickly, combine that to develop some and design some sophisticated complex processes. And so again, right, my hope is, or my message isn't that we need to make drastic changes to the curriculum. In fact, it's don't attempt to, right? If we try and do anything drastically, yeah, I always joke, right? When I teach process design, that chemical engineers have been successfully designing chemical plants for over 100 years, right? So there isn't necessarily anything wrong with what we're doing, right? It's more so that there's room for improvement. And so I don't want to completely rewrite the curriculum. I'm not asking you to go back and redesign all of your courses. My thought is, or my motivation and hope is, are there small changes that we can make in all of our core classes, right? That can have a compounding effect, right, on the performance of that student in their final design experience, a compounding effect on the confidence, right, of that student, right, when they finally get to senior year. On the next slide, I'm going to pass things over to Whitney, but one of the messages as well is, CHEMCAD is also here as a partner on this, right? Where what part of the solution might be is what would be of use to us as faculty, and are there, say, small modules that could be developed for all these courses that we could then readily implement in our courses and roll out and have other faculty adopt as well. So with that, I'm going to pass to Whitney.
Thanks for sharing all this information, Andrew. Can you go ahead and go to the next slide? So CHEMCAD is an intuitive process simulation software. We've been around for over 30 years. CHEMCAD is being used at over 100 universities worldwide. We also have CHEMCAD partners, which are our distributors worldwide. Can you go ahead and go to the next slide? The academic roots for CHEMCAD were originated from CHESS, which is a chemical engineering simulation system that was developed at the University of Houston. We're committed to education and supporting chemical engineering education through active partnership with universities to enhance learning and research. CHEMCAD is also an AICHE member, and we are sponsors. CHEMCAD actively participates in AICHE events, research, and sponsorships, including awards for service to chemical engineering education at the AICHE annual meeting. Can you go to the next slide, Andrew? On our website, you can find case studies and technical papers. We also have a section for academics on our website where you can see additional information. CHEMCAD has a YouTube channel where you can watch this webinar as well as additional webinars and other videos regarding CHEMCAD. If you'd like more information, you can request a live demo. And we also have evaluation licenses for professors at universities. That's the end of our presentation. If you have any questions, I'm going to go ahead and open up the Q&A. Andrew, we do have just a couple of questions in the Q&A. I'll just go ahead and read them to you. So a participant asked, is chemical engineering used in general biology? Are you able? You're muted.
So is chemical engineering used in general biology? Is that
yeah,
right?
The question is based on the information you presented, why is general biology not included as a chemical engineering course? That's his question. Is it included as a chemical engineering
Oh,
course? Is it not?
so I guess when I was laying out the general curriculum, say in terms of foundational courses, I just simplified it for presentation. So here, the students take a general biology course. It's part of actually satisfies their liberal ed or Miami plan requirement. Um, so our chemical engineers need to take a general biology course for graduation. And so I just didn't put in there for simplicity um, of the presentation of the curriculum.
Okay, so another question that we had is, can CHEMCAD be used for optimization, sorry, optimization of fermentation process of sugarcane molasses?
So
Would you like to share if you can do that in CHEMCAD?
um, so I haven't directly modeled a fermentation process in ChemCAD. So I guess the question would be is if you have, say, any sort of kinetic data, right? Then you should be able to. So I'm trying to think more in general, right? And so it depends on the level of detail. But if I'm just interested in, say, some steady state equilibrium process, so if you have equilibrium data for that fermentation process, well, then you could definitely model it in ChemCAD. If you had kinetic data, right, you could do that as well, and then you could get dynamic data as well. So the answer is yes, but what I would probably say is for a specific case like that, ChemCAD's not going to have internal built-in data, and so that's something that you would need to have and then implement it within the model. And it's not overly difficult. So if you have equilibrium data, right, the manual will take you through, the form of the equilibrium expressions that ChemCAD uses. And so then, even how to convert between different, forms or units to be able to implement within modeling that unit. And then same thing with kinetic data as well.
Okay, so another comment that we had from a participant was, are you able to share any, I guess, insight into procedures on specific tasks for simulations that are run by the student?
Yeah, so I guess in terms of tasks, so for example, what I've done in class is we'll often have, say, an interactive session where I'll demonstrate, say a ChemCAD simulation for a particular process, and then I'll record screencasts of me doing it within my office. So the students have that as a resource in case they miss any particular details. And then they also exist just there as resources. So I have a YouTube channel and I have, a playlist for when I've taught. Process design is where I put most of those under. And then I've shared that with, say, colleagues that are teaching mass and energy balance and want to introduce students to ChemCAD. Well, then they have, say, that video that they can, show students to get up and running for that first simulation.
I think that was all of the questions we had. Like I mentioned before, everybody will receive a copy of this presentation emailed to them. Attendees will also receive a certificate for your attendance. If you do have any other questions, you're more than welcome to email me. As you can see on the screen, my email is listed. And then if you want to visit the website, we have additional resources there for academics as well. Let me see. I think that's it. So that's the end of the webinar. Thank you everybody for attending, and thank you again, Andrew.
My pleasure. And if I can ever be of any help or encouragement to you, please just let me know. We're all in this together. So there's a